Hello, welcome to this video. This is 5-8, and today we are going to learn about the second derivative test, which will help us test for relative extrema. Alright, let's go ahead and dive in. This is going to be a two-part video. The first video, I'm going to look at functions with tables and graphs in order to utilize the second derivative test. And in the second video, we will make a comeback with implicit differentiation. Alright, so let's go ahead and figure out how we can use the second derivative test in order to help us determine relative extrema. Now, up until now, we have used the first derivative test in order to find relative extrema on a given function. Now, how we have done that is step one, we find where are the critical values for f of x. Remember, that's where f prime is equal to 0 or f prime is not differentiable or f prime does not exist. Secondly, what we did was we created and we analyzed a f prime sign chart to look for values, or we looked at a graph of f prime of x. And then what we did was we looked at those values we tested and we figured out, hey, if my function's increasing to decreasing, then there's a maximum. Or vice versa, if my function's decreasing to increasing, then that is a minimum. Now, the first derivative test is fairly straightforward and generally quick and easy to use. However, it doesn't always work. So we can use the first derivative test if two things are true. One, if we can be able to find the critical values. Two, if we are able to determine sign change. Of f prime of x. So what if we cannot use the first derivative test? Thankfully, there is another test that can be used to determine local or relative extrema. So we're going to go ahead and kind of highlight the basic idea behind the second derivative test here. Consider the function f of x, where we are not given an equation. I don't know anything about the function. However, I do know that f prime of 2 is equal to 0, and you'll see that here. F prime of 2 is equal to 0 in all of these cases. What does that tell us about f of x? Well, it just tells me that the slope there is 0. I have a candidate for a relative extrema, right? I could have a max, I could have a min, I could have nothing. It could be a saddle point, okay? What does it not tell you about f of x? Well, it just tells me that what I just said. I mean, I don't know if it's a max, a min, or neither. So let's go ahead and look at some certain situations. What if f double prime of x is positive? What if my graph is concave up like this? What is this? Well, then that is a minimum. This is a relative minimum. What if my function is downward facing? What if it is concave down? Well then, f of x has a relative maximum. Okay. And what if, let's just say it's a saddle point. Boop, boop, here. What if it's that case? Well then, that's neither. That case is neither. Okay, so in the example above, if we also knew that f double prime of 2 is equal to -5, what does this tell us about f of x? Well, if f double prime is negative, then this tells me that f double prime is concave down, at x equals 2. And it's going to look like case number 2, right up here, that it is concave down, and I have that horizontal tangent there at f of 2. Okay, so how does this help us with relative extrema? Well, if the second derivative can tell us concavity, if it's concave down, then if it's a critical value, that must be a maximum. If I have a critical value and it is concave up, then that must be a relative minimum. Because we can see here, concave up, if that's a critical value where f prime is equal to 0 or it's non-differentiable, that's going to be a minimum. So this is the idea behind the second derivative test for relative extrema. Okay, so let's go ahead and explicitly define the second derivative test. Consider the function f of x with f prime of c equal to 0. If f double prime of c is greater than 0, again, if the second derivative at a value is greater than 0, this is concave up. I can spell concave up. Okay, and then that's going, f of x is going to have a local minimum at x equals c by the second derivative test. Second example, what if f double prime of c is less than 0? Well, then that means it is concave down. And sometimes I forget, it's the maximum and minimum, so sometimes I like to just draw a quick parabola, concave up or concave down, and that's concave down. F of x has a local maximum at x equals c by the second derivative test. Okay? If f double prime of c is equal to 0, or if it's undefined, then the second derivative test is inconclusive, cannot be applied. Doesn't mean that it's not a maximum or not a minimum. You just cannot determine what's going on. You could go ahead and revert if you have the information to the first derivative test or some other method, but you cannot determine anything, okay? All right. Important. The second derivative test does not tell you inflection. It tells you about relative extrema. People often think the first derivative test, hey, that tells me increasing, decreasing extrema. Second derivative test, that must just tell me concavity and inflection points. No. The second derivative test tells you if you have relative extrema using the critical values from the first derivative test, okay? So you do determine concavity and inflection points using the second derivative, but the second derivative test helps you again with extrema. Here they are side by side, okay? And notice that some of the steps are similar, at least step number 1. Find where f prime of x is equal to 0 or undefined. That's the same. That is the same, okay? These are critical values of f. Secondly, we're going to go ahead and use a sign chart with the first derivative test, whereas the second derivative test, we just plug values straight into our second derivative. Sorry about that. Plug values into f double prime of x, okay? And then here's the explanation that we're going to go ahead and utilize today. The first derivative test is on the left, but I really want to focus on the second derivative test. F of x has a relative, and we can say maximum or minimum. It just depends upon what's going on at x equals c, because f prime of c equals 0. This is kind of part 1 of your explanation, and then part 2 is that f double prime of c is greater than 0. This means concave up, it's a minimum. If it was a maximum, f double prime of c would be less than 0. Okay? So, when should we use the second derivative test? Well, in most cases, we'll just use and apply the first derivative test in order to find values of x where f of x has local extrema. But there's 2 cases that appear on the AP exam that will require the second derivative test. And that's when you're working with a table of values, or you're working with an implicitly defined function with an, I think it's called an implicit curve. An implicit curve, okay? If your x's and y's are all mixed together. Like I said, the second video we'll do on this will focus on the implicit differentiation. Okay, so let's go ahead and dive in to example number 1. And here is the classic problem that you'll see on the AP test, usually on a multiple choice, possibly on a free response. The function f is twice differentiable with selected values of f, f prime, and f double prime given in the table above. Find any relative extrema on the graph of f of x. Well, in order to be a candidate for relative extrema, I'm looking for where is f prime of x equal to 0. Now this occurs at x is equal to 2 and 7. 2 and 7, because notice that their first derivative is equal to 0. I'm also looking for where my function is undefined. Is it undefined anywhere? Well, this table of values doesn't tell me that, okay? So I have two candidates here, and then I want to go ahead and I want to determine, you know, what are they? What are they? Are they a maximum or a minimum? Okay, and so what I'm going to do is I'm going to go ahead and I'm going to look at the second derivative, f double prime of 2. What's going on at f double prime of 2? Well, that is 4, and that value is greater than 0. So this is concave up, and if it's concave up, then that means that that point is a minimum. That's a minimum, okay? How about f double prime of 7? Well, f double prime of 7 is -3. And that is concave down, and then therefore that is a maximum. So I'm going to go ahead and respond here. I'm going to say f has a relative minimum at 2, 7. That's the point value, right? The function value, 2, 7. Because how do you know this? Because f prime of 2 is equal to 0, and f double prime of 2 is greater than 0. Okay? F has a relative maximum at 7, -2 because f prime of 7 is equal to 0, right? That's what makes it a candidate. And then how do I know it was concave down? And f double prime of 7 was less than 0. Okay, so it's concave down and therefore must be a maximum. All right, looking at this, some of my students said, why can't I just look at the first derivative? And I see that, hey, between 2, f prime of 1 is positive, and then f prime of 5 is negative. I'm going from a positive slope to a negative slope. That should be a maximum, not a minimum. Well, this is a table of values, and it gives you discrete information, point-by-point information. Notice I don't know what's going on between 1 and 2. I don't know what 1.77 is. I don't know what 0.9 is. And then furthermore, between 2 and 5, that's a lot of space. I don't know what's going on at 3. I don't know what's going on at 4, right? So all that information could change. That's why I can't specifically use my f prime, my first derivative test, to tell me that information. Let's go ahead and look at example number 2. The function f is twice differentiable for all real values of x and has exactly 2 critical values. Selected values for f prime, the derivative of f, are shown in the table above, along with the graph of f double prime, the second derivative of f. At which values of x does f of x have a critical point? Well, f of x has a critical point at x is equal to -3 and x is equal to +3 because f prime of x is equal to 0. Right? This information right here tells me, hey, that is a critical value. Again, undefined would also be a critical value, but I don't have anything there. For each critical point, determine if f has a local extrema at the given x value, or state if it cannot be determined. Well, the second derivative tells us this information. So at x equals 3, x equals, sorry, negative 3, that f double prime of negative 3 is a positive value. Positive value. That means it's concave up, which means that we have a minimum. Okay, so I'll state that in a moment. And then let's go ahead and look at f double prime of 3, which is here. Oh, f double prime of 3, well, that's 0. That's 0, so I cannot determine if that is a max or a minimum. Okay, so let's go ahead and state that. So we can say f of negative 3 is a minimum because f prime of negative 3 is equal to 0 and f double prime of negative 3 is greater than 0. Concave up has to be a minimum. Okay, how about f of 3? Well, f of 3 cannot be determined. Cannot be determined because f double prime of 3 is equal to 0. And I don't have any other information in order to determine that, okay? All right. Example 3. Let g and h be twice differentiable functions with g prime of x equaling h of x times x minus 2. The graph of h lies below the x-axis for all real values of x. Does the graph of g have a relative minimum, relative maximum, or neither at x equals 2? Give a reason for your example, or for your answer. Okay, this is a fun example. They tell us g prime of x is equal to h of x times x minus 2. If I'm going to have to differentiate that, I see product rule. They also tell us in this information here that the graph of h lies below the x-axis for all real values of x. So what this tells me is that h of x is negative for all values, okay? I don't know if that'll be useful or not, but we'll go ahead and see. They want us to determine if g has a relative minimum or a maximum at x is equal to 2. Okay, so in order to determine if we have a relative minimum, maximum, or neither at x equals 2, what I need to go ahead and first see is what is g prime of 2. I'm going to go ahead and I'm going to plug this in. H of 2 times 2 minus 2. Well, that's h of 2 times 0. So that's 0. Yes, it's a critical value. I know that the slope there is 0. Okay, well, what is now g double prime? G double prime of 2. And in order to find that, I first have to find out what's g double prime. So I'm going to take the derivative of my g prime. So we have the derivative of the first, h prime of x times x minus 2 plus the derivative of the second, 1 times h of x. I don't know why I put that parenthesis there. Okay. All right, so now I'm going to say what is g double prime of 2. I'm going to go ahead and plug this in. H prime of 2 times 2 minus 2. Well, that's 0. That's going to go ahead and kind of cancel out. Plus h of 2. And we know that h of 2 is below the x-axis. So it's negative. That means this is concave down. This tells us concave down, and therefore concave down, that's going to be a maximum. So we can say g has a relative maximum at x equals 2 because g prime of 2 is equal to 0 and g double prime of 2 is less than 0. All right, we're going to go ahead and look at the last example for this video here, example 4. The function of f of x is continuous for all real values of x. The table above includes information about f prime of x and f double prime of x for selected values and intervals of x. They say for each x equals -5 and x equals -2, determine if the graph of f has a local minimum, a local maximum, or neither. Explain your reasoning. Okay, well, the first issue that I have to look at is at x equals -5. What is the derivative there? Well, it looks like f prime of -5 is 0. Okay, and then what is the concavity of it? It's negative. It is negative. Okay, that means it is concave down, and that's going to be a maximum. I have a maximum there. Could I use the first derivative test? Well, I don't have any information about the first derivative left of -5, so I can't use that. Okay, let's go ahead and look at, actually we'll summarize that. So we'll say f has a local maximum at x equals -5 because f prime of -5 is 0 and f double prime of -5 is less than 0. Okay, now let's go ahead and look at -2. Let's look at -2. So I look at -2, f prime of -2 is 0. Okay, we have a candidate or critical value here. Now, what is the second derivative? Well, the second derivative is 0. Inconclusive. I cannot determine. But does that guarantee that it's neither a local min or a max? Let's go ahead and look at our first derivative. Our first derivative is negative. My function's decreasing on that interval all the way up until -2. All the way up, right? This is an interval. And then on the interval after, it's concave up. Hey, that's a local minimum. This is a local minimum. So I'm going to say f has a local min at x equals -2 because f prime changes from negative to positive at x equals -2. All right, B, find and classify any additional known values of x where f of x has a relative extrema. Support your answer. Okay, looking at the rest of our chart, it looks like at 3, the f prime does not exist and f double prime does not exist. Inconclusive data because I do not know if I'm increasing to decreasing or what's going on after 3. And then looking at 11 here, the first derivative is 3, so that's not a critical point, but 13 is. 13, f prime is equal to 0, and then the concavity is 1, that's concave up, making 13 a minimum. Okay, so I'm going to go ahead and state f has a local minimum at x equals 13 because f prime of 13 is equal to 0 and f double prime of 13 is greater than 0. It was 1, which means it's concave up, and that is a minimum. All right, C, at which values of x must the graph of f have a point of inflection? Go ahead and give your reason. Well, in order to have a point of inflection, our second derivative changes from positive to negative. So I'm going to go ahead and I'm going to look at my chart and I'm going to determine, all right, where do I change from a positive to a negative double prime? Okay, so f double prime is 0 at 2, and do I change from negative to positive? Yes, I do. Okay, how about at 3? Well, 3 does not exist, but we do change from positive to a negative. Okay, so there's a point of inflection as well. And then looking at 11, we change from a negative and eventually it goes to a positive. So that is going to be also a critical value or a point of inflection. Okay, so we're going to go ahead and say f has points of inflection at x equals -2, 3, and 11 because f double prime of x changes signs. All right, D. D is kind of a new concept in here that we have not talked about. Relatively straightforward with a simple explanation. They say the line tangent to the graph of f of x at x equals 6 is used to approximate f of 10. Will this approximation be an overestimate or an underestimate of f of 10? Explain your reasoning. And I want to go ahead and show you this tangent line approximation and just the overestimate or the underestimate. We have a tangent line t of x given in both of these examples and a function f of x. And go ahead and notice here t of x. If this is my function, my tangent line, and I'm predicting what's going to be the output at 4, notice how t of 4 is an overestimate of f of 4. And in this example here at 4, t of 4 is an underestimate of f of 4. So my tangent line approximations, are they going to be an overestimate or an underestimate? Well, that really depends upon their concavity. So when explaining why a tangent line is an over and underestimate, be sure to state that f of x is concave up or concave down over an interval and not just at that point, okay? So let's go ahead and look at this example. They want to know the graph at f of x at x equals 6 used to approximate f of 10. So let's go ahead and see what is going on here. If we look at our graph on the interval 3 to 11, well, our graph is concave down, okay? And just to give you an idea here, concave down, if I had a tangent line, let's say at 6, say it could be something like this, my tangent line approximation is going to be an overestimate. It's going to be way more than what the actual function value is because it's concave down. So it's an overestimate, okay? So let's go ahead and look at an explanation here. The tangent line approximation of f of 10 will be an overestimate because f double prime of x is less than 0 on the interval, and it was 3 to 10. No, 3 to 11. 3 to 11, meaning f of x is concave down. Okay? Awesome. There you have it. All right, that's going to do it for this video on the second derivative test. We'll go ahead and do a second video on how to use the second derivative test with implicit differentiation. Give me a thumbs up, like the video. Catch you in the next one. See ya.